Okay, so today I want to talk about ANOVA, and the goal here is ANCOVA, I should say, analysis of covariance. We'll start with just a discussion about ANOVA. So ANOVA is an analysis where we're looking at a variety of groups, and we want to know whether or not there's a difference in whatever our dependent variable is based on these groups. So we might have something like four different levels of body mass index, and we want to know if there's a difference in depression. So we would run what's known as an ANOVA. When we do ANOVA, we do conduct post hoc testing in most cases because we want to know if two of the groups differ somewhere. When we do ANOVA just tests for an overall difference, but it doesn't look for specific differences among variables. Okay, so in order to test for those specific differences, we have to do post hoc testing. Actually, I'm going to forego the focus on ANOVA here, and I'm going to go straight to ANCOVA since we've already done ANOVA in the previous versions of this course, but ANCOVA will cover it anyway. Um, so for here's an example where we can look at, say, four levels of BMI and see if people with different levels of BMI differ on self-esteem. So that would be an example with ANOVA. Again, I'm going to go straight to ANCOVA instead. With with any of these analysis, whether it's ANOVA, ANCOVA, one thing we'll do is we try to provide a measure of effect. You'll always have, if you're consulting for a client, your clients will always ask you, was this, yes, this is significant, but is it meaningful? And meaningful is generally determined by a practitioner in the field. Like if you're talking about a psychotherapist, the therapist might want to know if the differences between groups of body mass index and self-esteem are meaningful. Because with statistics, we know the larger the sample size, the more likely we would have a significant result. Those significant results aren't always meaningful. One way we can quantify meaningfulness is through an effect size. Effect sizes aren't something that a clinician uses in general. A clinician uses her experience to determine the nature of the effect, but an attempt to quantify that is known as an effect size. So it's the best we can do statistically. So the ones that we use for ANOVA or ANCOVA is our eta square and partial eta square. So eta square is the proportion of the total variance accounted for by the effect. So you can see that the sum of square of the effect, sum of squares that's attributable to the effect, like the effect of the independent variable divided by the total effect. So that's a proportion there. And we have heuristics for strength. Small effect is around 0.01, medium effect is above 0.06, and then large effect is anything that's 0.14 or greater. Partial eta for eta squared looks really just at that effect, like what proportion of the effect plus the error. So it's the effect plus the errors. We're not doing the total effect. We're looking at the effect of that particular variable plus error in general is anything that we didn't assess in our model. So it's a little bit different than the two than the I'm sorry than during the eta square. The eta square is the one that's generally reported more so, but partial eta square uses the same heuristics 0, 1, 0, 6, and 14. Another one that you don't see as much is omega squared, but I know I was tutoring a student and her professor kept on, requiring them to do omega square. That's the letter omega. By the way, that's the letter eta. So you should always know what letters you're reading. So this is sum of square effects minus the degrees of freedom effect times the mean square error. So we had to calculate that by hand for that student, but it uses the same heuristic. So you may get this on, or you can request it for sure when you're conducting your analysis. Let's do ANCOVA. Okay, ANCOVA stands for, like I said, analysis of covariance. I highlighted the acronym letters and where they come from. What we're doing here is we're trying to, and I write it as purify, to purify the variance in the dependent variable, because we really want to know what's the impact of our predictor on the dependent variable. But what we'd like to do is just limit the variance in the dependent variable to that which can be affected by our predictor. So to do so, we eliminate any variance that's attributable to some other, some other confounding variable. Or actually, I'll call it a covariate here. What we'd like, and the reason I say that is because we know confounding variables are related to both the predictor and the outcome. What we'd like is to have this variable only related to the outcome, not the predictor at all. In fact, that's one of the assumptions of ANCOVA is that it's not related to the independent variable. So, but it's okay if it is, right? It's okay if it is, and all you do is analyze that effect. So this is what we're going to do here. So we're going to use this my first data set. We're going to assess the effect of quad BMI on self-esteem, but we're going to control for depression. So let's go ahead and do that. So in this case, we're hoping that, and we're going to use this process called proc GLM, general linear model, and we're going to hope that, I think it might be generalized linear model. We're hoping that this variable depression is unrelated to BMI, but we're going to allow it for it to be related, and we're going to analyze it if it is. So we have to set our dependent variable as a class variable here, so it's known that it's our independent variable, so that we know that it is categorical. And I set the reference level at 0, so everything will be compared to 0. So we'll create dummy variables from this, right? So 1 will be related compared to 0, 2 will be compared to 0, 3 will be compared to 0 in terms of in terms of depression, in terms of the effects on self-esteem. All right. So here, I mean, I could have also done this as quad BMI. I could have added another term here. So I could have had self-esteem equals quad BMI and then quad BMI times depression for the interaction. But I can use this I forget what they call these lines here in computer terminology, but you can use this straight line in order to indicate that you're going to have this covariate and that we're doing an interaction. I'm also asking for confidence intervals, and then I'm looking at for the means of BMI, the adjusted means for BMI as well. I'm also going to get the P values, and I'm going to do post hoc comparisons if there are differences in BMI and effect of BMI on self-esteem. We're going to use a Bonferroni correction. So I'm assuming you know what that is, but a Bonferroni correction just essentially divides whatever your alpha is by the number of comparisons being made so that you have an overall comparison of, say, 0.05. So it's adjusting that for all the comparisons. So let's go ahead and run this. All right, it says here BMI has 4 levels, 1, 2, 3, 0. So we're comparing everything to 0. You get a lot of your usual ANOVA tables that you would get for any analysis of variance or any kind of regression type model. And ANOVA is like a regression model because you have an outcome and you have a predictor. You got our R squared here, so this model accounts for 50% of the variance. Pretty good. And so then we get these parts of the model here they just tell us whether or not we have effects that are significant, but what we're really looking for is to get the parameter estimates. So that's what we want, and that's what we get here. So in this case, we get, and this is our model, we have our intercept, we have our BMI values because we're comparing 1 to 0, 2 to 0, 3 to 0. Those are their intercepts, or excuse me, the slopes for those model components. Then we also do the same with depression. So there's depression by itself. So it has a significant effect. But because, let's see, because the interaction, let's see, this one interaction is significant, we wouldn't interpret this main effect here. We're going to look at this effect. So there's one of the effects is significant. So this is the effect of the highest level of BMI versus the lowest level of BMI times depression has a significant effect on self-esteem, but the other levels of BMI didn't. Okay, so that's important here. And we see even here when we look at simple main effects, that level of BMI had a significant effect. But again, we're not interpreting that because once the the interaction term is significant, we focus on that. And one thing I like about proc GLM here is we get this nice picture making the comparison so you can see what's going on. As you can see, there's crossing of lines. This is what's prototypical when you have an interaction that's significant. It has them on different colors too. So it has, well, we're looking at, say, this looks like it's green. So it's level 3. That's the highest level. And we can see that, yeah, self-esteem declines the most when we're at the highest level of depression, right? More so than it does for the other levels, right? Like there's 1, and we actually have 0 as well. I think this is 0, is this dark one, and then 2. So again, so you can see that the impact of as depression goes higher, self-esteem decreases for everybody, but more so for those in the highest level of body mass index. Pretty cool. So again, here's our means adjusted for LS stands for least squares, means adjusted for our different levels of body mass index. So you can see that self-esteem is lowest over here, right? 488.306360022, right? Okay. Pretty low too if you're have low if you have low levels of BMI too, right? Okay, what else? Okay. There you go. That's yeah, some other interesting tables. Differences in alpha, Bonferroni adjusted, not significant, significant. I think this one isn't as telling as the nice figure here. Okay. Yeah, so that's with controlling for depression. The reason I controlled for depression is because depression and self-esteem are are critically they are important they're sorry, they're very highly correlated to one another. Okay, let's go back to the see what else did I wanted to do. So we would write up our results. We assess the relation between BMI, quartiles, and self-esteem, controlling for depression. The results of the data analysis suggest a significant depression by BMI interaction. Probing the interaction, we find that comparing highest BMI to lowest BMI, the depression by BMI interaction is significant. And you get the T value, the P value. You always write the T value, the P value, and then the confidence interval here, the 90. This is a 95% confidence interval, all of which you can get from our table here, right? I was able to get everything out of here, right? For this interaction, I was able to get the T value, 2 - 2.48, the p-value, and then the confidence interval. That's what I use to report that. I would include this picture in the result too, because it's really, really nice. Although it is color, and you might not be able to always publish a color picture without paying extra money for it. And it's actually true. So let's assess the effect of quad BMI on self-esteem controlling for sex instead. All right, let's do that. Use sex instead of depression. Sex. Do I have depression anywhere else here? All right, take a look. Let's see if there anything else happens here. We got quad BMI, so we're not worried about that yet. So here we don't have a significant interaction, so we don't need to probe this interaction at all and look at the differences. It's irrelevant. So we're not even going to look at these. All these p-values are huge, right? The only thing then we'd look at is, and then sex itself doesn't have a significant effect, but it appears, well, in this model there are no, well, let's see, the closest one is body mass index level 3 versus 0, it's 0.09. That would, be significant at an alpha of 0.10, but because the sample size is large, has 380 individuals after we. So, by the way, the reason this is different is because even though the data set has 393 individuals, when we put the analysis in, if any participants have missing values on any of the variables in the model, it'll delete them. It's called list-wise deletion of missing data. So you'd have 13 people lost here, but 380 is still a large sample size. And this model, the overall model is not significant. Our p-value for the overall model is 0.1158. And then all these other probabilities, like your quad BMI itself, is only significant at alpha 0.10, which is too high for us. So really, we don't look at anything. I mean, we do see a little bit of a crossing for the green value, so 3, but I mean, you'd think it's significant, but really it's not. Okay. We just checked everything and we saw that. All right, so that's how we run these. So let me take a look real quick at running just a general analysis ANOVA, but using proc GLM. But I'm going to eliminate this. Okay. There's a proc ANOVA, but let me see if I can run it with proc GLM as well. Yeah, there you go. Same thing. So this is, but this one, no, wait, this one includes, no, it doesn't include sex in the model, right? So we're just looking at, so this was the first item I had on the list. We're just looking at BMI, and whether or not it affects our outcome variable self-esteem. And everything's being, so it's 1 versus 0, 2 versus 0, 3 versus 0. And here, just by itself, we do not have a significant effect. Again, our p-value is 0.0559 for the effect 1 versus 0. So the way BMI went was 0 is the lowest. So I divided it into quartiles. So if 0 is the lowest, 1 is the second lowest, B is the third lowest, and fourth is the highest level of BMI, right? You can take a look at this figure here so you see where the different levels of BMI, how they affect self-esteem. Yeah, this is a box whisker plot. This is the interquartile range, the middle 50%, and this is the median. Right, so you can see that there's not a lot of difference there. This must be the mean. I don't know what that stands for, but I'm assuming it's the mean. Here's some outliers. So there really isn't an effect here. Interestingly, when we did include the covariate, the first covariate, when we included depression in the model, we had a lot of significant effects. So you have to, somebody might say, well, it's not worth looking at because we had nothing significant here. But we know that, like I said, depression and self-esteem are strongly correlated. So I probably would have done this in the first place and would have gotten this interesting result. There you go. So this is one way you can do an ANOVA or an ANCOVA using SAS. So again, ANCOVA, we're trying to eliminate or purify the variance in our dependent variable. But remember, the key assumption is that the covariate is unrelated to the independent variable, but if it is, you probe the interaction. You get some interesting results. Like we saw for when we use depression, we saw nothing when we use sex as a covariate. All right, cool. Practice. Thank you.